It's in continuation. Let's start today. Work done in adiabatic process, right? We have also derived the formulas for work done in previous cases also. Let's just stick to adiabatic process, right? So students see here, due to expansion, initially the piston was at the dotted position. Now it came to this position. This, let the displacement is dx, right? So the work done by the gas will be dw is equal to force into displacement, that is force is equal to pressure into area, so that is p into dv, correct? A is the cross sectional area of the piston and dv, that is equal to a dot dx, जो volume है, that is area of the container into displacement dx, correct? Yes or no? Student, suppose the gas expands adiabatically, total heat is constant, right? Temperature not constant, heat is constant means heat neither can exchange through the gas medium, right? So here gas expands, right? Gas expands, let the gas expands adiabatically. The gas expands adiabatically from initial state P1, V1, T1 to final state P2, V2, T2. Okay. So work done during adiabatic process. Initial work done, if I'll say W adia is equal to PdV, and the volume changing from V1 to V2, correct? Yes or no? And for adiabatic change, students, you know PV to the power class we have derived this one in the last lecture. You see PV to the power gamma is equal to K, है कि नहीं? और ये भी हमने किए थे P is equal to KV to the power minus gamma, right? If we will go to that side, correct? So here let's
Yes, sir.
let's find the work done in the adiabatic process. So that is equal to V1 to V2 KV to the power minus gamma into dV. In place of P we put, right? Correct? So that is going to be, students, if K will come out, yes or no? And we're interested to find the integration of V to the power minus gamma dV. Sorry, 1 minute. This is V to the power minus gamma into dV, correct? So that is K is equal to V to the power 1 minus gamma divided by 1 minus gamma, correct? And limit V1 to V2. If I'll put the formula here, I can get, that is K 1 by gamma came out. This is V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma, correct? So that is equal to 1 by gamma minus 1 whole into KV1 to the power 1 minus gamma minus KV2 1 minus gamma. Are you getting, students? I multiplied.
Sir,
Square.
so that will be V2 minus V1.
1 minus gamma is there. One minus gamma is there. V2 minus V1. Yes, I wrote V2 to the power 1 minus gamma by V1 to the power 1 minus gamma. And here I made na 1 minus gamma was there. Here I made 1 gamma minus 1 na. Correct? I took a negative sign common.
Yes, sir. Yes, sir.
Okay. So that will be 1 by. But here you see we can directly modify now it. K is equal to how much? P1 V1 to the power gamma, that is equal to P2 V2 to the power gamma, right? So W adia is equal to 1 by gamma minus 1, correct? P1 V1 gamma V1 1 minus gamma minus P2 V2 gamma V2 to the power 1 minus gamma. Understood, student? By putting the value of K. Got or not? So finally, the expression you keep in mind, work done during adiabatic process is equal to 1 by gamma minus 1, right? See here, student, V1 gamma, V1 1 minus gamma. then it will be how much? Only V1, na? Correct or not? So finally we got that is 1 by gamma minus 1 P1 V1 minus P2 V2. Students understood how to find the work done in adiabatic process?
Yes.
And this can be also modified if I'll be writing P1 V1 is equal to nRT1 let, right? And P2 V2 is equal to nRT2. Correct? Na? So work done by adiabatic process is equal to 1 by gamma minus 1 whole into nRT1 minus nRT2. Are you getting my point, students? So here, by taking this nr common, you can also write in another form of adiabatic work done. That is nr by gamma minus 1 whole into T1 minus T2. Correct or not, students? Understood? All understood up to this? All?
Yes.
So, student, next, let's start with first law of thermodynamics applied to isochoric process, applied to a cyclic process, and applied to a isobaric process. Isobaric process. In isobaric process, we'll see about next how it can be applied to boiling process and how it can be applied to melting process. We can see that. Okay. It's a very interesting part. Let now give heading. First law of thermodynamics, right? First law of thermodynamics applied to isochoric process. First law of thermodynamics applied to isochoric process. Students, you know, isochoric process means what? What is constant? Volume constant, student. Isochoric process means what? Volume constant, right?
Yes, sir.
So no change in volume means dV is equal to 0. And you know work done is equal to P into delta V. So that will be also equal to 0. है कि नहीं? And you know from first law of thermodynamics, Q is equal to how much? Change in internal energy plus work done, na? And change in internal energy plus work done is 0. So that is equal to U, delta U, right? So in isochoric process, the entire heat is given to or taken from the system goes to change its internal energy. Yes or no? So how much heat we are giving directly getting converted to what? Change in its internal energy. Yes or no?
Yes, sir.
Change in its internal energy. Right. And that Q is constant volume. We can write N CV delta T molar specific heat, right? We can write this or not? Got, student? First law of thermodynamics applied to isochoric process. Yes or no, students?
Yes, sir.
Next, let's see to first law of thermodynamics applied to a cyclic process. First law of, I'll share the notes, don't worry. First law of thermodynamics. First law of thermodynamics applied to applied to a cyclic process. You may get varieties of question applied to a cyclic process. First law of thermodynamics applied to a cyclic process, right? Students, in a cyclic process, you know, the system returns to its initial state after undergoing a series of changes, right or not? Students, है कि नहीं? Cyclic process means what?
Yes, sir.
Comes back to the original position. So here what happens? Internal energy in a state function. So no change in internal energy. Finally, it coming back to the original position means delta U is equal to 0. No change in internal energy because it started from a state and it again came back to the same state. So the total energy is maintained, right? No change in internal energy. So that's why your first law of thermodynamics was delta U plus W. So that will be 0 plus W, right? So that means Q is equal to W, na, students? In a cyclic process. So in a cyclic process, we can conclude the total heat, right? The total heat absorbed by a system is equal to the work done by the system. Is equal to the work done by the system. Students got it? Then let's go to first law of thermodynamics applied to isobaric process, right? First law of thermodynamics applied to isobaric process. First law of thermodynamics applied to isobaric process, right, student? Students, see here, isobaric process. Isobaric process means pressure is constant, right? Yes or no? Students, isobaric means pressure constant. Are you getting all? Students, let pressure remains constant. P is constant. At constant P, volume changes from V1 to V2. Listening now, my voice is audible.
Yes, audible.
V1 to V2.
Yes, sir.
Very small thing, not that much difficult. You have to keep all the information in mind so that you can attend a numerical, right? So that is P into V2 minus V1, correct? And you know that PV is equal to nRT, na students? So we can write W is equal to nR into T2 minus T1. Got, students? Work done during first law of thermodynamics applied to isobaric process, right? Understood or not, students? So that means an isobaric process, the absorbed heat partially increased in internal energy and partially to do work, right? Here, we can conclude here, the absorbed heat in this process, the absorbed heat in this process, the absorbed heat goes partly to increase internal energy and partly to do work. And partly to do work. Got it, students? Then let's see, students, how the first law of thermodynamics to determine the change in internal energy during the boiling process and melting process, right? How to find first law of thermodynamics to, we'll see next, the last part of this theory, today's lecture, right? See here, first law of thermodynamics, first law of thermodynamics to determine the change in internal energy, to determine the change in internal energy during boiling process, during boiling process. Correct, students? Students, see, student, let m mass, let m mass of liquid is heated at the temperature of its boiling point, so that it changes into vapor at a pressure P. M mass, we just m mass of liquid heated, right? Vapor pressure P, and let Vi is the volume of the liquid जब हमने गर्म करना शुरू किया, right? This is volume of liquid and it will be converted to steam or vapor. So let Vf is volume of vapor. Let it is volume of vapor, correct? Getting the students? So the work done by the liquid in this expansion, because volume is changing definitely. So delta W is equal to how much? P into delta V, that is equal to vapor volume minus liquid volume. And student, let latent heat you know. L be the heat of vaporization, right? L be the heat of vaporization, latent heat of vaporization, heat of vaporization. So that means the amount of heat required for vaporize, that is dq is equal to ml. You remember student? Latent heat of vaporization, right? Yes or no? And let जब liquid था, जब volume vi था, तो तब internal energy u था. Let that is initial internal energy. Initial internal energy. And जब उसने वेपर हो गया तो उसी टाइम पे इंटरनल एनर्जी चेंज हुआ, लेट दैट इज फाइनल इंटरनल एनर्जी. That is final internal energy. Are you listening on? So that means you can write delta Q is equal to first law of thermodynamics, delta U plus delta W. Yes or no? You remember this law? And delta Q
Yes.
is equal to ml, and delta U is equal to final in internal energy minus initial internal energy, plus you got delta dW is equal to V P Vf minus Vi, correct? So that is UF minus UI is equal to ML minus P into Vf minus Vi, correct? Students, can you use this expression for finding the change in internal energy during boiling process, right? So if you know student, M will be given in the question, latent heat will be given, pressure will be given, vapor will be given. Sorry, volume, initial volume and final volume of vapor will be given. P vapor and V initial will be given. So can you find the change in internal energy? Understood all? This formula will be remembered. Palvi, Pragya, Priyanka, Narayan, Nafish.
Yes, sir.
Next student, let's see the same process in melting process to find the work done. Melting process, right? Student, melting process, let in the same way, m mass of liquid, m mass of solid, sorry. Solid to liquid is known as melting, na students? M mass of solid is heated at its melting point. When solid melts, the change in its volume, let delta V. That is negligible small, right? That is negligible small. Change in volume means ice will multiply, correct or not student? It will be converted, but the volume will remain almost same. Getting the students? So L be the, and you know, so work done is how much students? Always you know dW is equal to P into delta V, and no change in volume, so work done is equal to 0. But here, let L be the latent heat of fusion, students. You know, when it is melting, so L will be latent heat of fusion, correct?
Excuse me, sir.
Uh,
Sir, after charge, what you have written?
Latent heat of fusion, negligible small. Did delta V is negligibly small.
Sir, after charge.
Change in volume. That is
Yes, sir.
change in volume. dW is equal to PdV. So no change in volume. So work done is equal to 0. And you know latent heat of fusion concept, delta Q is equal to how much? Why ml, right? And there is no change in volume. So but there will be change in internal energy. Let initially जब solid था ये मेरा initial internal energy था, and initial internal energy, it was initial internal energy, and UF final internal energy, final internal energy. So we can write delta Q is equal to how much? Delta U plus delta W. So that is ml is equal to UF minus UI, because work done is almost 0. So that is UF minus UY in melting process. You can directly find by multiplying M into L. Got, students? So an internal energy of a system increases by ml during the melting process. All got this theory part, students? Students all got now this part?
Yes, sir.
We'll do examples on in today's next class. Okay. Next today we'll go for heat engine and limitations of first law of thermodynamics and what is second law of thermodynamics and Carnot cycle. Right. Another 1 or 2 class will complete this one. Then we'll go to kinetic theory of gases. Okay. I'm sharing the notes. You update it today. Okay, students.
Yes, sir.
Hmm.